Hello students, good morning. Today we will discuss about the magnetic field of solenoid. In 11th standard we have already discussed about the solenoid. We know the structure of solenoid and how the solenoids work and how the magnetic field develop inside the solenoid and outside the solenoid. So here, current carrying solenoid, a structure or figure is shown here. I is a current passing through solenoid. This figure is already discussed in 11th class. So, solenoid, it is a device. Solenoid is a device or solenoid is a long insulated copper wire wound in the form of helix. Now, solenoid is a long insulated copper wire. It is the copper wire and this copper wire is wound in the form of helix. As shown in figure, the structure of solenoid is shown here. This is the copper wire through which current flows and this is wound in the form of helix. This helix is formed here and this is the current passing through this copper wire, and this copper wire is insulated, and due to the current passing through this solenoid, a magnetic field is developed inside the solenoid and the outside the solenoid. For ideal solenoid or real solenoid, the magnetic field at the axis of solenoid or inside near the axis of solenoid is uniform. This is the axis of solenoid and here the magnetic field is uniform and therefore these magnetic lines of force shown here are parallel to each other inside the solenoid. The ideal solenoid is, this solenoid is a long helix and the diameter of this solenoid is very small as compared to its length. Suppose this is maybe solenoid, the length of this solenoid is as like this and diameter will be as like this. Therefore, the diameter of solenoid is very small as compared to this length, and this ideal solenoid has a magnetic field uniform inside the solenoid near the axis of solenoid, and the magnetic lines of force are parallel inside the solenoid and outside the solenoid they are widely spaced. Therefore, we can say that the magnetic field outside the solenoid is less as compared to inside the solenoid. It is maximum at the axis of solenoid. Now we can discuss about the solenoid and the magnetic field developed due to the current passing through the solenoid. For real solenoid, the finite length, the magnetic field is uniform and has good conducting strength at center and comparatively weak at the outside the coil. This is the coil-like structure and the magnetic field strength is strong inside near the axis of solenoid and it is comparatively weak the outside the solenoid. From this figure we can say that the magnetic field lines are widely spaced outside the solenoid, whereas inside the solenoid the magnetic line of force are parallel. Therefore, strength of magnetic field also maximum inside the solenoid. Here we will apply the Ampere's law to find the magnetic field inside the solenoid and outside the solenoid. To apply the Ampere's law, here figure is shown. Ampere's law is applied to a long ideal solenoid as shown in figure. This line, this dot in indicates that the current is coming out of the plane of paper, and this cross, symbol of cross, indicates that the current is going into the plane of paper. This is the direction of current. We can say here, or we can observe this direction, and we can say that this current is coming out of plane of paper, and here the current is going into the plane of paper. And another figure is shown here, an Ampere loop. This A, B, C, D, A. This closed loop is shown. We can say the Ampere loop here, A, B, C, D. And this is the direction of integration, or we can say the direction of Ampere loop. The magnetic line of force are shown here. This is the direction of magnetic line of force. And the direction of current is shown by this dotted and the cross. Now we have to apply the Ampere's law for this solenoid. Now we know that for the application of Ampere's law, we have drawn here Amperian loop. Now apply the Ampere's law for this loop. By the Ampere's law, we know that the line integration of magnetic field over a closed loop is given by, or is equal to mu naught, the total current encircled by the loop. Mu naught times the total current encircled by the loop. Now this loop is considered here. Now the magnetic field, a line integration of magnetic field over a closed loop is equal to mu naught times the total current encircled by this loop. When we apply the Ampere's law to this loop, we will apply the Ampere's law first at all on this line AB, then on line BC, then line CD, and then consider line D. Therefore, the total magnetic field due to this closed loop will be equal to, or we can say that the over the rectangular loop ABCD, the above integration can take place as like this: integration magnetic field. We can apply this Ampere's law for first at all for this line AB. Therefore, this limit will be A to B, and total magnetic field will be equal to magnetic field on this line AB plus BC plus CD plus DA. Therefore, we can take integration magnetic field B into dl over a line BC plus magnetic field over a line CD plus D into dl over a line DA, and this will be equal to mu naught times the current. Mu naught times the current. Now, here in this equation, I is the net current encircled by this loop. This I is the net current encircled by this loop by the Ampere's law. Now the magnetic field on the line BC, here this line BC and line DA, the direction of magnetic field and the length are perpendicular to each other. The magnetic field, direction of magnetic field is perpendicular to line BC as well as it is perpendicular to line DA. Therefore, when we take the magnetic field, then the B into dl or the dot product of magnetic field and dl, it will be equal to 0 because the angle between magnetic field and the length is equal to 0, and therefore the integration, second integration and plus third this fourth integration, this will be equal to 0. That is B into dl, vector B into dl in limit of B to C and in limit B to A. These two terms will be equal to 0 because the magnetic field, direction of magnetic field and the length is perpendicular to each other. Therefore, it will be equal to angle between this length and magnetic field is 90 degree, and therefore the magnetic field on this line will be equal to 0. Therefore, integration over this line BC and DA will be equal to 0. Now, CD, considering the integration over line CD, this line is out of the solenoid. This line is out of the solenoid, and we know that out of the solenoid the magnetic lines of force are widely spaced, and therefore it is negligible. Here the magnetic field is negligible, and therefore this term will also become equal to 0. That is, the magnetic field, unlike CD, will be equal to 0, and therefore these all terms becomes 0, and we can take the integration over the line AB, B into dl, and this will be equal to B. Integration of dl is equal to L. L is the length of line AB. Therefore, we can write here B into L. B is the magnetic field, and this term will be equal to 0. This term will be equal to 0 plus this term also will be equal to 0, and this will equal to mu naught times the total current encircled by the loop. Therefore, we can say that B into L is equal to mu naught R. Now, we can consider here N, that is small n, the number of turns. N is the number of turns per unit length of solenoid. N is the number of turns per unit length of the solenoid. Here we have find out the magnetic field over one length AB or over a closed loop, Ampere loop, is equal to mu naught I. Now we have to find out the total magnetic field due to the current in the solenoid. To find the total magnetic field inside the solenoid, consider N is the number of turns per unit length. This number of turns per unit length is equal to small n. Therefore, and I flowing through the wire. Therefore, the total current encircled by the loop, that is I. Here, this I is the net current encircled by this loop, or the current which is going or coming out of the plane of paper, and I is the current flowing through the wire. Therefore, I is equal to N into N into I. N is the number of turns per unit length. Therefore, the total turns on the length L is equal to L into N, and the total current coming out of the plane of paper is equal to I. Therefore, the net current encircled by the loop is equal to I is equal to L into N into I. We can put this value in this equation, then we get B into L is equal to mu naught N into N into I. We have put the value of I in this equation, then this L will be cancelled. Therefore, the magnetic field will equal to mu naught N I. This is the formula of magnetic field inside the solenoid. From this equation, we can obtain the magnetic field for ideal solenoid. That is, the magnetic field inside the solenoid can be obtained by using this equation, where mu naught is the constant value, that is, it is equal to 4 pi into 10 raised to minus 7. Here small n is the number of turns, and I is the current passing through the coil or current passing through the wire. Okay, now we will discuss about the toroid by using the Ampere's law. Okay. Now we will discuss about the magnetic field of a toroid. Now we have discussed the magnetic field of solenoid. That is, magnetic field of solenoid is equal to B is equal to mu naught N I by using the Ampere's law. Now toroid, this toroid is a solenoid. Toroid is nothing but the solenoid. But when this solenoid, a finite length, is bent into a hollow circular tube, then it is called a toroid. Toroid is as like same a solenoid along straight as like a helix structure, and when this solenoid is bent as like this coil is when bent, then it is called as the toroid. Toroid is a solenoid of finite length which is bent into a hollow circular tube as like a tire, a rubber tire of the vehicle. Same like a structure of toroid. Here a structure of toroid is shown. The Ampere loop along the central axis of toroid. We have to find out the magnetic field at the central axis of the toroid. is the wire wound along this toroid. This symbol indicates that the current is coming out of plane of paper, and this cross symbol indicates that current is going into the plane of paper. Here, Ampere loop is considered. The direction of this Ampere loop is as clockwise direction. R is the distance of this point on this Ampere loop, or we can also say the radius of this circular Ampere loop. Now the current, this current coming out of the plane of paper and current going into plane of paper. We have to apply the Ampere's law to find the magnetic field at the central axis of toroid. Now we know that the magnetic field or line integration of magnetic field over a closed loop is given by mu naught I, where I is the current enclosed or encircled by the Ampere loop. This is the Ampere loop. Now we know that I is the small I is the current passing through the wire, and here is the number of turns. Capital N is the number of turns, and small I is the current in wire. Therefore, we can say the current I is equal to N into I. Put this value in this equation, then we get B dot dl is equal to mu naught Ni. Now, taking integration, B dot into dl, we can get B into integration of dl. Integration of dl, it means the total length of this circle, and the total length of this circular loop or Ampere loop can be given by 2 pi into r, and therefore B into 2 pi r is equal to mu naught N I. Therefore, by using this equation, we can find out the formula of B is equal to mu naught Ni upon 2 pi r. This is the magnetic field at the central axis of solenoid, or when we consider this Ampere loop, the magnetic field closed over a closed loop is equal to mu naught Ni upon 2 pi r, where this N is the number of turns, I is the current in the wire, and R is the radius of Ampere loop. From this equation, we can say that the magnetic field is not uniform inside the toroid. It is inversely proportional to R. As we consider an Ampere loop, here as like will be changed. It will be less than that of this loop. That is, the magnetic field over this loop will be equal to or will be less than at the point on this another Ampere loop. That is, the magnetic field is not uniform here, or we can say that the magnetic field is inversely proportional to R. Thus, unlike the solenoid, the magnetic field is not constant over the cross section of the solenoid. It is inversely proportional to R. And today we will discuss about the solenoid as well as toroid. Now, the magnetic field due to current, the chapter magnetic field due to the current is finished here.